Hello, welcome. My name's Todd. I work at Google. I've been working on machine learning SRE for a very long time. And I'd like to tell you a little story of how we got here, how I got here from my perspective, and then also try to use that to understand where we might be and where we might be going. So the title of the talk, SRE for machine learning. So the topic is, how do we do reliability and production engineering on machine learning systems? That is something that sometimes people are now calling ML ops, operations work on ML systems. Not really wedded to names, but we have been calling it ML SRE for a good number of years. So I want to talk a little bit about what that means for us, what we've done to get here, why we're here, and maybe where we're going. So let's talk about the first 10 years and maybe the next 10, or at least what some part of the next 10 might be. So here's the agenda. SRE for machine learning is not really that new. I think it is expanding quickly now, and so many of you and many people are hearing about it for the first time. But it dates back more than 10 years in my personal experience, and there may be those of you who have been doing this sort of reliability engineering work on machine learning systems for longer than that. So don't want to take away from anyone else's experience. So I'll talk about my experience back in 2008-9, becoming aware of and beginning to work on large-scale machine learning systems from a reliability engineering point of view, and then look at what's happened in the last decade and how that might help us decide what we should do in the next decade from now. So in particular, I don't want to be making so much predictions exactly about what will happen, but some guesses about what probably will happen and how we should think about that. So I will do a brief introduction of what machine learning is. I want to say super clearly, like, I'm not an ML expert. That seems funny to say, right? Here I am, like, I'm giving a keynote at a thingy that's got ML in the title. I'm not a machine learning expert, and I think most people who work on the productionization of machine learning systems are not or shouldn't have to be. I'm not saying that this is not available for all of us to learn. Like, the math is tractable, and it is possible for most of us to understand this sort of things, but it's not required, and sometimes it's not even useful. So I'll do a brief introduction to roughly what machine learning is and just mention a few terms, just to make sure that for those of you who are newer to this space, we're on the same page, you're able to follow along. If you are new to this space, welcome. It's a great place to be. We're pretty welcoming. There's a lot of fun here. Don't let the super serious PhDs and people who are very serious about model architectures and algorithms dissuade you. There's a ton of room for a lot of different kinds of people with skills, including people with just regular SRE skills. So welcome. And hopefully you'll find it to be a welcoming and interesting community to be a part of. I'll talk about where SRE started. I'll talk about how ML SRE typically starts, or how ML systems get their start, the specific motivation for what kinds of work we do, and then at the very end, just a little snippet, I'll try to predict the future, as one does in these talks. Luckily, this is not recorded or anything, so you can't hold me to it. No, unfortunately, this is recorded. You are going to hold me to it. So I'm going to do my best to be careful and say true things. We'll see how this all goes. So let's start with, as we should, some greetings. So these are my typical questions. For those of you who have ever seen a talk by me, I usually ask, who am I and who are you? It's meant a little bit as a joke, but also sort of serious. It's nice for you to know literally anything about me when you listen to me, so that you can figure out, like, you know, in what context to see the ridiculousness that may be coming out of my mouth. And it's useful for you to know how I'm thinking about you as an audience. Like, this is strange for me to be recording this talk with none of you out there. So I have to imagine who you are. So let me tell you what I'm imagining. Let me tell you, like, who I think you are. So who am I? I'm a recovering and systems and network engineer. So I did systems and network engineering for a long time before I got into the ML space. I was kind of duped into, or fell into, founding the ads ML SRE team, formerly called Smartass SRE, best name ever, at Google a little over 12 years ago. At the time, I didn't know what machine learning or SRE were. So if you find yourself in either of those positions, you can do fun stuff anyway. So don't let that hold you back. I founded and I still currently lead the ML SRE team globally at Google. And I also lead the Pittsburgh site for Google. Pittsburgh, Pennsylvania has a pretty decent size, around 500 to 1,000 people engineering site for Google. I'm working on a book on reliable machine learning for O'Reilly with a bunch of other people. A couple of chapters are already available online. In my other talk in SREcon, we had a link to where to get those. So feel free to contact me and I'll provide a link to early access chapters. Single most important thing, all of you ask, I don't know what the animal is going to be yet. The animal has not been determined yet. I am waiting to hear what the animal is. I'll keep you posted. Next, I'm talking about who are you? So you, I believe, are SREs who've heard a bunch of hype about machine learning, but may not have used it in anger on purpose, but are still sort of wondering what it's good for and how we all got here. So anywhere at that level or above that level of experience, you should be able to get something interesting out of this talk. If not, skip to the end. There'll be donuts. I don't know. There'll be donuts if you've bought yourself donuts. This whole virtual conference thing is a bit strange, isn't it? So why are we here? We're here to demystify the past, sort of explore it. I think many people think machine learning is brand new, but it's not brand new. And there's some things we can learn from what, not just Google, but other companies have done over the last, 10 years or so that we can help decide where we should collectively go. And I think SREs have a big part to play in there. So where are we going? Well, that, mis compañeros, is the question. So stick along for the ride. We'll see if we can figure that out. Good. So super brief segue into what again is machine learning? What again is AI? So here's the classic joke. The difference between machine learning and AI is if it's written in Python, it's probably ML. If it's written in PowerPoint, it's probably AI. That is not fair, but that is funny. I will just say, Matt is this is a funny thing to say. So seriously, what is it, and does that distinction really matter? So as many of you have heard me say and seen in other places, AI is a family of technologies and approaches, could be vision, could be algorithmic stuff, could be all sorts of things designed to create machines and machine systems that can demonstrate intelligence, whatever we mean exactly by that we normally associate with humans. Okay. Ideally, this would include something like learning and something like problem solving. Okay, so that's AI. Machine learning is the study of algorithms that enable computer systems to solve some specific problem or task by learning from data. So machine learning is almost always, I think always, a building block for AI, but insufficient by itself to accomplish anything we would call AI. Today is mostly about machine learning. We're not talking about the complex systems that people might call AI. Most of what most people are doing and most of what's getting a lot of the attention and a lot of the systems work is machine learning. So we're concerned with algorithms that learn from examples. So a quick concrete example, how do we tell the difference between an apple and an orange? You can just do it. I can just do it. That's intelligence. No, I don't know what that is, but maybe it's intelligence. But if you want to program a computer vision system to do it, it gets complicated pretty fast because you think it's red and orange, but there are green apples, but there are also green oranges. So you think it's smooth versus bumpy, but those little water droplets look kind of bumpy when you're doing vision process. And some oranges are pretty smooth. Anyway, it gets pretty complicated pretty quickly. The simple thing is to get really complicated early and just build a system that learns from examples. So ML is a set of strategies that build up data structures that get updated by looking at data with labels, and then it's used to categorize other data. My SREcon21 Dublin talk had a little bit more context, but there's hundreds of examples from, hundreds of introductions from people much more talented than me that can help you understand a little bit more detail about ML. Let me introduce some specific terminology that I do plan to use though. So there's a type of machine learning, which is a very common type of machine learning called supervised learning. So supervised learning, what it does is it takes, first of all, a set of examples that have labels. So what is an example? An example is a piece of data, which is of the type of thing we would like to categorize or predict. So if we are trying to look at pictures and determine whether those pictures are apples, oranges, or neither, a picture would be an example. So what's a label? A label is the true answer or the correct answer for that example. So if we take a label of apple and we put it on a picture of an apple, that is a labeled example. Okay, so this feels like it's giving names to pretty obvious things, but they're names that are used commonly in the industry. And I just wanted to expose them early on so that if they're used later in the presentation, you can continue to follow along at home. Good. So what's a feature? We're going to talk about features occasionally, and people talk about features all the time. Features are a fact about the example that are relevant to our predictions. So color might be a feature, or shape might be a feature. This is an aspect of the example that we find to be relevant to the prediction or categorization we're trying to make. A model, as I said, is a data structure of what we think we've learned so far. And then a learning system reads examples, looks at the labels of those examples, and updates the model based on them in order to try to represent a set of weights or a set of connections that will help us correctly predict, correctly categorize future instances. So that was a little bit fast. Doesn't really matter if that all made sense. Hopefully, we won't talk in any significant detail about this. The main thing we're going to do is talk about the shape of a system that does this, not the actual doing of this itself. So let's take a big step back. Forget about the computers for a second. We're coming back to the computers. There's going to be stuff about computers. Don't worry. Take a big step back and let me tell you about where machine learning where SRE for machine learning started, geographically where, but also contextually and organizationally where. So in my life, SRE for machine learning started in Pittsburgh, Pennsylvania. So it started on the Google Ads quality team. So there was a famous set of t-shirts they had printed up, Google Ads quality, we use math. So what was Google Ads quality? This was a team designed to build tools that ultimately ended up using machine learning and quite a lot of machine learning to target ads. Now, I will acknowledge this sounds a little bit creepy or weird or something. This is neither creepy or weird. This is amazing. So when you do, let's just talk about the simplest search case. When you do a search, you would ideally like no ads or ads that are at least directly relevant to the search that you just did and to your interests at that time. So finding the ads that match your interests at that moment that you're doing the search is critical to the success of search. And it actually has been critical to the success of Google over time. It's one of the most important contributors to the early success of Google. So we should only show relevant ads. Google and other people only charge for an ad that we've shown when somebody clicks on it. So there's no interest in showing you an ad you don't care about because that wastes our time and money. And it's not valuable to you. It annoys the user. It provides zero benefit to the advertiser and zero money to Google. So the collective set of that is pretty bad. So we use machine learning to do that. So why? Okay, so there are a set of teams who were building ML models and deploying them in production. Why bother putting SRE on this set of teams? Like SRE at the time at Google already worked on the ad serving system. They already worked on some of the storage systems, on the scheduling and cluster management system. They worked on many other systems, including other data systems in ads. But why would they work on the machine learning system? Well, mostly for the consequences of it not working right. So good ads make money and make the users happy, and bad ads cost money and make the user sad. Google looked at that, and Google Ads quality folks looked at that and said, we think we could use some SREs to make this work more reliably, more predictably. Okay, and hence was born SRE, Ads ML SRE, nay Smart Ads SRE, such a great name. The Smart Ads Serving and Selection System or something like that. So fantastic name, since changed, I miss it. And why Pittsburgh? Just out of curiosity, I thought this before I moved there. I'm not from Pittsburgh. I grew up in Puerto Rico. So the Pittsburgh thing was a little bit odd to me. I didn't know a lot about the city. Love it now. Fantastic place to live. It's sort of the Sheffield of the US. But at the time, I didn't know anything about it. Well, Carnegie Mellon is one of the most storied places in universities globally for machine learning. They've been doing more work on more different types of machine learning and more focus on machine learning than computer science departments or schools in most places. So as a result, Pittsburgh was the place to do it. Google had a lot of machine learning talent already starting to locate themselves in Pittsburgh. So good. Let's just give you a super high level view of what the system architecture is, just so you can understand the kinds of tasks. If you were an SRE and you're like, I got to make this stuff work, what is it that I'm making work? What is the scope of what I would need to do? Well, we ingest some data. So we find some data, we get some data, we read some data, we put it in some format. We pre-process the data. So we clean it up and we get some metrics about it. Not sort of super clear. We don't need to worry about exactly what those metrics are, but we need to know distributions of the data or big changes in the data. And I'll talk a little bit later about why that might be. We have a training system that reads the data and updates the model somewhere. We have a quality system that checks the results of what the training system just did. And if they're good enough, we have a serving system that does inference on those models. So, okay, sounds good. All of this is backed by a set of model management and pipeline orchestration systems they track metadata about models and feature and data. So that's essentially what we do. For a lot more detail on this, you should have seen, I hope you have seen, Mary McGlowan's talk on demystifying machine learning in production. It's got way more detail. If you missed that talk, and it talks about similar systems, by the way, Mary and I have worked on some of the same systems. So if you missed that talk, wait for the videos to come out and please go take a look at it because it is fantastic and worth seeing. And it will give you much more detail on this. So now we sort of know the where and the what. Like we're productionizing that system. We're doing it for ads. We're doing it in Pittsburgh. Sort of think yourself into that state. We're doing it in the, just around 2010 is, you can think yourself like back in the halcyon day. Now, I don't know that 2010 was the halcyon days of anything. The US was still trying to creep out of the housing collapse. Tech was doing strange. I don't remember what tech was doing, but it was a strange time in our industry and certainly a strange time in the US. And that's where we were. And we're getting started on this SRE for ML thing. How? Which is like, in particular, like, what are we going to do? How are we going to approach this? And how does this start? Well, let's take a step back and see how there came to be a system to work on at all. This is an interesting sort of thought experiment that can demonstrate the thinking that produces this set of results. So in my experience, not just at Google, but talking to other organizations and talking to some of you, almost no one says, hey, I'm going to build a machine learning orchestration, training, serving system from scratch. What generally has happened so far in our industry is someone wants to train a model. Why do they want to train a model? Well, they have some compelling application for training that model. They want to find the things in the picture or understand the spoken words of the users or determine the key that a song is in. They have an application that they want to do, and they realize that machine learning is appropriate for that application. Fine. So they build a model. And over time, like the model doesn't usually, I say, and it works. Okay, so that's cutting out a little spot in the middle where the model doesn't work and they have to figure out why and improve it and improve it and improve it. But often it is the case that over time, the model kind of works and we want it to work much better. And so we iterate and we troubleshoot and then we improve the model, and we iterate again, and then we train on new data, and then we troubleshoot, and then we measure, and then we iterate again. And as we're doing that, what we find is it's worth our time to make some scaffolding and some infrastructure to help us retrain a model with slightly different configurations, to help us do hyperparameter exploration. Don't worry about what that means. It means basically tweaking some configurations about how the model is trained and how the model is set up. Doesn't matter what that is, but just imagine there's some values we can pick. It's unclear how to pick those values. What if we had a system that picked those values for us? Sounds good, right? Well, we need a system to do that. What about picking which features to add? Like, I want to predict whether this is an apple or not an apple. What if the time of day? What if people are more likely to upload apple pictures in the morning than in the evening? I don't know that. I might not guess that. I'm suspecting that's not true, by the way, but it might be true. And if it were true, I would want a way to discover that. So there's some automatic feature exploration systems maybe we build. And over time, we build up enough little pieces to help our model development process that what we have is something where we can deploy the model repeatedly and hopefully repeatably into production. And that's a system. Cool, we got a system. We started with one model and built up a little system. Okay, what happens then? In my experience, what happens is success is a little bit contagious. So other teams notice, hey, that system over there works. I should probably try to use it. Okay. They want their models trained and evaluated and tested and deployed and served just as reliably as the original team. Okay, so they show up and they try to piggyback on the system. Now, what usually happens is their models don't look exactly the same as the other model, and then everybody's got some choices to make. They try to convince the people who built the system to just tweak that system just a little bit for them. You know, that might happen. Or they try to tweak their models to fit into the system better. That might happen as well. In all of these cases, we start seeing multiple different models from multiple different teams training on the same system. And now, if we're meeting all those model types and all those model teams, what we have is a multi-model, multi-tenant machine learning platform. And this is how ML platforms have historically grown up. One application that's worth it. They make enough investment to make it work. That investment is attractive. Other teams show up. Okay. So now at this point in time, you sort of understand how we get machine learning platforms. I've talked to you about why Google Ads Quality wanted to apply machine learning, apply SRE to machine learning. Let's talk about a little bit more in general about why people do that. So again, we have a platform. The thing I want to mention again is you really do need to watch Mary's talk. If you didn't watch Mary's talk and you missed it yesterday, please do watch it as soon as possible. She covers in much more detail the kind of things you need to know about what an ML platform looks like, how it breaks, and some best techniques for approaching, mitigating, and avoiding those failures. And so that is her talk is the bread and butter of like what it is to make an ML platform work well. So I'm going to assume that if you haven't seen that, I'm going to pretend you have seen that and hope that you see it very soon and tell you that now that you've watched that, see what I did there? Now that you have watched that, what you'll know, you should know what an ML platform looks like what its components are, how it fails, and a few techniques for preventing and mitigating those failures. So, okay, we're all set there. That sounds good. So let's talk for a second about, well, what is an ML platform then? What does it need to run well? Well, to one extent, and a pretty significant extent, a machine learning platform is just another distributed system. Okay, it needs, and this should be unsurprising to all of you, it needs capacity planning. Okay, it needs monitoring, it needs deployments of binaries and deployments of models and deployments of data. So papering over some complexity there, and it needs testing. And by testing, I mean binary, like code release testing, but also several other kinds of testing. And it needs incident response, hardening, robustification. I don't know if robustification is a word, but it needs some robustification, and it needs automation, because we don't want to do these things by hand. So this is mostly, not entirely, but mostly just regular, perhaps even boring, perhaps not, SRE stuff. So for those of you who have no background in machine learning, you should take heart here saying, I can do that stuff. Like, it will be odd to do that stuff in a new context, but for most of us, that's true no matter what. For most of us, it's true that it's odd to do some of these things in a new context anyway. So what makes machine learning SRE harder or uniquely hard compared to other kinds of SRE? Well, there's one thing that we want more than almost anything else, which is we're trying to balance between two very different things. And this is a thing, by the way, that other systems have to balance as well. But the course of this looks pretty different in machine learning than in other kinds of distributed systems or other kinds of storage systems or serving systems. And I'll try to talk about exactly why. But new models and new teams need flexibility, and they need a lot of flexibility. So put yourself in the position of someone who's been asked to solve a pretty novel problem for some business or organizational unit. So you're trying to solve, how many Slack messages will customers send tomorrow? I don't know. I could do some kind of, I've heard these words, linear regression. Maybe I just do a linear regression on how many messages they did. They're like, yeah, but how do you break the users down into categories? I don't know. Some sort of key means thing, some sort of clustering. There's got to be some naive clustering thing. And at some point, you're trying to solve some problem like that and many other different problems within your organizational scope. And at some point, you'll just say, like, I'm going to break out the machine learning and see what it can do. As you do that, you need a lot of flexibility about what kinds of knobs and what kinds of data and what kinds of model architectures you can bring to solve the problem. That sounds fine. So you might need custom model architectures. You might need the easy addition of new features because you're going to add new data into the mix all the time. You probably need super fast deployments. And those models, like if you are doing that, you want that model, if it breaks, to notify you. Like you're not depending upon it yet. You're just trying to figure out how to make a model that works. But you will do that most quickly when you are using a system that facilitates that. Okay, so you have that level. But then once you find a system that works, you want to very, very quickly get that system into production with as little work as possible. So you want reliable training and serving. You want automatic capacity available to be provisioned for your model. You want SREs to support you when something goes wrong and like you don't know how to fix the production part of it. So you want all of that with very little friction. This is a pretty tall order, in particular because the flexibility that you take advantage of in the first phase is working against the rapid standardization in the second phase. It's not quite true. In particular, what I'll observe is if there is a system that supports most of these things relatively well, there's a view of this where this is the same system operating at different service levels. So one of the service levels at the beginning is everything works fast, but not with as much reliability. And the second is everything works with lots of reliability, but perhaps not as fast. And we'll talk for a second about what that looks like. Let me take one other big step to look at the shape of the SRE problem here. So the biggest problem that we face in machine learning SRE is model quality. So what is model quality? Model quality is, does the model work? How is it working? For whom does it work? How well does it work? Okay, so I acknowledge that as a vague way of describing it. There's much more detailed ways of describing it, but most people are able to capture the general idea. So who handles model quality problems? So, and how do we discover them and how do we escalate them? Well, so the obvious answer, and throughout the history of machine learning SRE, this was the answer we tried to use only partially successfully for the longest period of time, was model developers handle model quality. So our position for a long time was we operate a system. The system provides a set of throughput, and the system provides a set of data availability, and the system provides a set of, capacity, and the system provides latency on inference and capacity on inference. But the actual values in the model and how well the model works, that's not our problem. Like it can't be our problem because we don't build the models. So an analogy here would be like, if I operate a system that does data analytics or data processing, and you want to make me responsible for whether your dashboard shows revenue for last month correctly. Like, nope. Like, I operate a system that adds up revenue and puts it in a little pie chart or some other sort of little line graph. You operate the system that builds the pie chart or the line graph. If those are wrong, that's on you. If the system doesn't work at all, or I add the numbers wrong, that's on me. Okay, so there's the analogy. This doesn't work that well in machine learning. So the obvious answer is we try to make model developers responsible for this. They certainly are in a position to troubleshoot it. And certainly many of the causes of model quality problems are due to model developer errors or model developer choices. However, and here's the unfortunate thing, once models are stable, what we find when we look at the situation, and Daniel Papazian and I did a look at this and published some of the results last year. Many, but not all, of the quality problems in models that show up are caused by systems issues. So they can be caused by resource shortfalls, pipeline stalls, data unavailability, server misconfiguration. None of these are about the architecture of the model itself. The model does not change, and yet the values in the model do. This is where the glory and terribleness of machine learning comes from. So what I will tell you is responsibility for model quality is one of the big unsolved problems in machine learning SRE. There's some really interesting thought around this, but whoever makes the most progress on this particular problem is going to be able to control the future of machine learning SRE. That is my predictions. Figure out how to solve this, and everything gets easier and better for almost everyone, but it's really hard to solve this. So I'll set that aside. Just give you something to think about there. So let's look at one big idea of how we might be able to address that problem. So, and some of this does relate to how we did try to address this problem. So there's think back to the situation I described where we want rapid experimentation, but then we want support in production. And we have people, we have end users and modeling teams using the same system. So in the early stages, they experiment. There's no SRE support other than that the system basically worked, but no SRE support for the model. And people iterate and they experiment, and most models never go anywhere. But as a model launches or gets promoted into production, we would want some promotion to production to involve a higher level of service, which would include incident response from SRE, but also better and different monitoring, better and different capacity availability, different thresholds for alerting, et cetera. Okay, how do we do that? Like, how would we promote something to from experimentation to production? Well, not too glibly, like everything else we do, we start by doing it by hand so we can figure out what we want. What are the problems? What are the things we need to check? And in particular, we need to make a list of what would count as making a model eligible for promotion to production. So, initially we would have model owners train and evaluate and serve models with no external approvals whatsoever, but also almost no support. So very minimal service level objectives. After some set of things, as I say, some set of things about a model is true, it can get promoted to production upon request and get production support. Okay, and now what set of things? Like very next question, it's sitting right there. I know you're thinking about it. What is the set of things? Well, basically that the model works. There. Is that sufficiently clear? No, of course it's not sufficiently clear. So what set of metrics do mean that it works? Well, to some extent, start with measuring what you would respond to. So what are the things, and this is difficult to answer in the abstract because it can only be answered for a class of models or a specific machine learning platform. And I'll acknowledge that's a little bit of an interesting statement. That statement is true right now, or at least I claim it to be true, but it's a little bit unfortunate that it is true. But what would we respond to? Well, things we would respond to include the data are incomplete. The data are too big, they're too small. They have a different distribution on some subset of the data. Sometimes we call that a slice of the data. The training is running too slow, or it's stuck, or it's gone strange in a particular way in terms of just reading the data and outputting the new values in the model. That there's some significant change in model quality, that training is using a lot more resources, or that serving is using a lot more resources than it used to. That the model won't load into serving, that there's something about the configuration or the size or the values or the operations that are in the model that mean that serving's not able to read it and use it. Or that the model's now suddenly slow in serving. So this is not an exhaustive set, but here are some pretty obvious things where if we set up some monitoring on the models and these things are firing alerts, we are not ready to promote this model to production. This model, something is still strange about it. So we set objectives for these, and then we measure the model's performance according to them, and we promote models that are doing okay on this respect. Now, there's other things that might be included, like having an available contact for the model if the model goes bad, having metadata about the model and the prerequisites or the dependencies of the model. So there's a bunch of other things we can and should do, but the point is to figure out, like, what do we need to know about the model in order to be happy to support it in production? Okay. And then in theory, the reliability of a model is, in theory, automatically determinable. So for models that are retrained regularly, this is easy. Just retrain the model a bunch. And once it works reliably, once it's, retrained reliably the last N times over M periods or whatever, you're just like, I don't know, that model pretty much works. I'll set up paging on it because it's okay. For other models, this is a little bit harder. There's some work going on in the data analytics space to do similar sort of analysis. But if we want to provide production support on the training of a model that will only basically be trained once or very infrequently, it's going to be difficult to have enough history to know that we can do that. The general idea is to try to find an equivalence class for that model. So if that model is derived from or very similar to some other set of models, then perhaps we can make an equivalence between its predicted reliability and that of other models. So this is a subject for future work. It's an interesting area. Let me point out one last thing about this. Speed matters here. It matters a lot. So it doesn't matter that your ML system be flexible and fast just for the bragging rights. Machine learning speed turns directly into innovation. So innovation requires iteration in machine learning, and in most cases, an iteration requires speed. So as we explore and we iterate, the faster we can try out ideas and rule them out as bad, or try ideas and refine them into good ones, the more progress we'll make. Only the very best machine learning systems will have high reliability and speed. That's where you want to be spending your time. So careful engineering, thoughtful monitoring, great abstractions, and well-trained incident response are all required for speed, and speed is required for innovation. So SRE for machine learning is not an effort in saving money or avoiding potential embarrassment or avoiding damage to users. It is, of course, all of those, but fundamentally, SRE for machine learning is about enabling innovation, which is why we do machine learning in the first place. Okay, so I talked for a long time about stuff we do and how we think about what we do. Let me talk briefly about what's next. So here's what I claim is the work to be done and what's going to happen. I think we're going to make machine learning boring. And I want to say again, because I don't know that it was ever boring. Maybe it's boring for some people. It's not boring for me, but I think we need to make it boring. So 5 big things I'm hoping will happen. 1, organizations are going to start accepting older machine learning technology and auto ML approaches because they're good enough. So right now we see most people trying to adopt the very cutting edge of ML technologies. That's fantastic. That's exciting. It's mostly a waste of most people's times. Standard, pretty straightforward modeling approaches and prediction approaches are better for most people most of the time, and they're cheaper and they're easier. And we're going to start to see organizations accept that because the value is high. 2, platforms are finally going to converge in features. Like, what do they cover? What do they produce? Sorry, not machine learning features, but software engineering features, and stabilize. So right now, like, there are very, very few complete end-to-end platforms. Most of the things that call themselves platforms cover overlapping subsets of the kinds of work you need to do. And so no one who's in this space has sort of like an end-to-end environment that's exactly the same as anyone else in this space, because everybody is assembling their own platform. This is sort of back when we were making our own database, making our own window managers, and adding features to our own window managers. I'm like, at some point, I just want a few icons on the screen, and I want a set of key bindings, and I want a set of window control and tiling systems, and I don't want to have to build this from scratch. We're going to get to that point, and I hope we get to that point in the next few years. Training and serving costs are going to plummet, which is fantastic, which means more people will be able to access this stuff. APIs to integrate machine learning into applications will finally stabilize and become ubiquitous. So it'll be easy for you to say, I don't care who does it or how it happens, but I need to give you a thing and you tell me what kind of thing that thing is from this set of things. And that's the kind of API we're going to see spread almost everywhere. And here's an infrastructure thing that's super boring, but super important. Model quality evaluation is going to be a standard part of machine learning platforms. It will become ubiquitous. And as a result, we're going to be able to trust the results of the platforms much more because we'll know what's in the models and we'll be able to depend upon them. So those are my 5 big things that I think will happen. Here's one thing for you all to think about. I think all SRE teams are going to do ML. So think back, like, storage management and being able to deal with storage isn't a thing for storage teams. Like, everybody has to deal with some amount of storage. I think boring ML, once it works well, is going to be everywhere. It is going to be a thing that integrates into almost every application. These platforms are going to work well enough that they will push this stuff, at least on a simple basis, to ubiquity. And so almost every team will have some part of the applications and the systems they support using machine learning. Do I think we're ready for that? Not even remotely. But I think that if people like, Mary and people who are working on production ML systems do their jobs so that we keep pushing for standard and simple solutions, I think people like the rest of us are going to be able to consume and use those solutions eventually in a much, much easier fashion. So with that, I will close. Thank you so much for your time and attention. I know this was a bit of a whirlwind tour. I'm super happy to have been able to, walk you through at least a little bit of the last, I said 10, but it's really about 12 plus years of machine learning SRE work. And hopefully I'll see many more of you in the future. Thanks for your time.